Alright, so there's one aspect that I want to talk about now. That is, once we've gone and computed everything for this example problem, and even for this example problem, this one here. Okay, and this is what I want to do is I'm going to give this as a task for you to do, because I want you to verify it for yourself. I'm going to talk you through it, but the question that I want to ask is, what is the reaction force here? What is the reaction force here? Okay, so this is an important, very important question, because that's also something that we still can compute after the fact. Okay, so let me talk you through this. Let's start with this single finite element that we did a couple of days ago. So let's start with this example problem first, the one where I applied a load here, and I want to ask what is the reaction force on that side. Okay, so recall when we solved this system, we had some rows that had a W of 0 associated with it because the displacements were known. All those rows are rows essentially of equilibrium equations that we've not used. Okay, and for us to be able to compute our reaction forces, all that you have to do is take those rows, okay, and multiply it with the load vector, and that's equal to whatever is there, whatever is in this loading, plus some unknown there, which is a reaction. So maybe I'm going to do is maybe I'll do a part here that is going to be in maybe in a what I'll do is maybe I'll do a small part here that is going to be in a notebook. Okay, just to solidify things. Let me just maybe go here. So what I want to show you is what will happen if I multiply this row equals to that what is in that right hand side, and I'm going to add a new variable in. So I want to just write this first equation out first, the one that's associated with this W1 that's 0. Okay, because at all of these W's ones that are zeros, we can after the fact use them to go and compute the reaction forces at those associated nodes. Okay, so let's go 87.5. So let me type that in there. So let's say import numpy as np. Let's say let's call it reaction equation is equal to np.array 87.5 10.5 and minus 98. All of this times 1 is 6. Yeah, the right hand side is essentially the force associated with the equilibrium equation. In this case it's just 0 plus some unknown reaction. So that's how you should view this right hand side. So this equation is this will get multiplied by this, okay, equals to whatever is there plus some unknown reaction. Okay, so if I want to know what the unknown reaction, that's the equation that I want to solve. So I can say our equation so let me just put it down here. Our equation is equal to F equation. So what I can do is to say to isolate the unknown reaction, it's going to be equal to F equation minus 0. If I take this 0 towards that side, that's it. Okay, so I just want to, this is just to show you more or less. I'm going to leave it as comments rather, and say that is the F equation is then essentially I'm going to call it F equation not reaction, not unknown. So I'm going to take whatever is the non-unknown part of this equation and dump it into a variable, and I'm going to call this 0. Okay, and if I want to know, go and compute the unknown reaction, I can just say it's essentially the reaction equation, and this is still not multiplied with Q. So let's do that. So let's just put Q in here. So we get actually compute the equation and not just the terms of the matrix. So at the moment I've got that, but I haven't got it with multiplied with Q. So let's just go and look at what the displacements were. So these were the solutions. So Q is 0, 3.3 So you can then verify for yourself that these values come from that which we've computed. 1.4 1e minus 5. Okay, that's what we have. And now I can say this reaction equation is just np dot that time comma q. And let's see what is this print unknown reaction. And before I'm going to print it, I'm going to first ask, what is our expectation? Our expectation is we applied a load of 1,000 newtons to this side. My expectation is the reaction must be 1,000 this side. Minus 1,000 is what I expect to see as the answer. And there I see minus 1,000. This is, as a matter of fact, it's exactly minus 1,000. But because my displacements that I used here are rounded off to 3.3 and 1.4. There's a couple of things beyond there as well. So this is why it just looks like this. But if you were to compute it numerically, solve the problem numerically, and not just use this sort of rounded versions of displacement, this will evaluate exactly to minus 1,000. Okay, that is important to understand. Okay, so this takes me back just to maybe just quickly, before I go into the next example, just to quickly talk about one thing, and that is when you look at this equation here, this is Newton per meter times Newton is equal to forces. And I just want you to, in future, when you look at this system, this stiffness matrix and the unknown displacements and the right hand side loads, all that you need to, the way you need to interpret it is that each row, yeah, is associated of an equilibrium at a node. That is essentially it. I'll talk on this on Monday in a little bit more detail, but I just want you to sensitize you already for this. Each row is essentially associated with a equilibrium, nodal equilibrium at a node. That's what it is, boils down to. And so when I look at this first row is associated with W1. So that is the equilibrium equation associated, associated at, let me just go back, node 1. The second equation would be equilibrium at this node, and third equation would be equilibrium at this node. This is important to understand. So what we've done is and the one thing that's awesome is that this equilibrium equation, the nodal equilibrium equation, is satisfied exactly. Okay, so when it comes to the finite element method, what we are doing is, and you know already now, I mean, from these solutions here, that from the sort of internal forces that are like this, that the continuum problem is not an equilibrium. It's only equilibrium in an average sense, like we've clarified that. But what we've done is we've taken a problem that is difficult, the continuum problem, that we can only approximate equilibrium for. What the finite element does is to say, take that problem that we can't solve the equilibrium for exactly, we can only approximate it, transform it to a discrete problem. Transform it to a discrete problem like this, kq equals to f. Okay, so this is after I've now taken derivatives with respect to the w's. Take it to a discrete form, and when we solve for equilibrium of this discrete form, we'll solve the equilibrium at each of these nodes to be exactly satisfied. And that is quite beautiful. That is quite an interesting one. So the nodal equilibriums are satisfied exactly, because this is essentially why this equation is indeed equals to this on the right hand side, not just approximately. And this, as you can see for yourself, this equation, force equilibrium at node 1 is equal to the reaction force. Okay, and we just the reaction force is something we do after the fact, because when we compute it, there's a W1 that's 0 there. But every time when there's a W1 0, it means there should actually be a variable additive there after the fact when we compute for reactions. And this equation, this multiplied by this, is exactly 1,000. This multiplied by this is exactly 0. So that's exact equilibrium. So that's just food for thought. That's a beautiful way to think about what the finite method does, is take a problem that's in the continuum world, we only approximate, and let's break it down to a world where we can satisfy that exactly. And I realize I have not switched to my Jupyter notebook, so I apologize for that. Let me just switch to the Jupyter. All I did in the Jupyter notebook was the following. Oh, this is going to be a crazy video. Okay. I set up the Q's 0, 3.3, 1.4. I set up the equation for the equilibrium as my values in my the row in that stiffness matrix, dotted with Q. That's my equation. So, no man, this is not good. Okay, doesn't matter. So what I did was what I tried to explain was, it seems without actually showing the screen, so I apologize for that, was that F equilibrium is equal to 0 plus some unknown. And this 0 is because in that force vector at node 0, there's a 0 in there. So that's, and then there's an unknown reaction that we have not put in as a variable, but that's also part of that thing there. And then we essentially have the equilibrium equation. It's just essentially, we could solve for this from knowing that the equilibrium equation must be equal to the right hand side, this force equation. So I can isolate that force equation. So the unknown reaction is F is essentially the equilibrium equation, yeah, which is this one, minus the 0, which comes from this right hand side of that force equation. Okay, so that's essentially that. So I'm going to go back to this PDF just to highlight that again. So there's that 0 from that force side. This, so what we have is this times this is equal to 0 plus an unknown reaction. And then the unknown reaction is equal to this times this minus this. Okay, that's how we can go about solving for the unknown reactions. So that should be clear. Let's go then to the body force example. Okay, and this one I'm not going to compute on the notebook. I'm rather just going to stick to the PDF here and show you that you can go and compute it yourself. But again, this unknown reaction force, we can go and you please go and verify for me the following. If I take this times this, it's equal to whatever is the load there plus an unknown reaction, and then go and compute what is the unknown reaction. So the unknown reaction will be this times this minus whatever is that non-zero loading that's associated with that node needs to go towards this side, and that will be something that is quite close to the actual force. In fact, it will be exact if you use the right numbers here, not just the rounded off numbers. It will validate exactly, and also for this. But if you use approximate rounded off numbers here and here, don't expect to get it 100% exact, but do expect that it's very close to what you would see. And what would my expectation be for the reaction force here? My expectation for the reaction force there would be the weight of this bar. Done. Okay, the weight of this bar is this times the area times the length. And this is how we go and then compute the reactions after we've solved the problem as well. So now we've got everything. We can, after we've got the displacement field, we can compute strain, we can compute the stress, internal force, and all the reactions at the nodes at which we had prescribed displacements.